everyone. This is Chris again. So just to double check if anybody can hear from me. Okay, awesome. So, okay, let me share my screen. Where's my deck? Okay. There we go. Okay, before I get started, just to double check the screen's working and the video's working, so on and so forth. Can you see my share point? Hey guys, are you able to see my screen with the title How to Win Kaggle Computation? Okay, all right, awesome. Okay, cool. Yeah, thank you so much, everyone, again, so for taking time to join us at the How to Win a Kaggle computation session. And I guess this is going to be the last session of this Nano course, and hopefully you guys have enjoyed the content so far and had to get a chance to put your hands on the Kaggle computation. Yeah, so this is pretty much what I looking for you guys to do. But today I'm particularly excited because to be honest, this is my favorite session because so for the previous ones, so they're probably too technical, and so listening someone to talk about some technical details, it's not fun, believe it or not. So but today, so I'm going to talk to demonstrate some actual use cases. Well, for the previous courses was still using actual cases, but the today is going to be special because I will be talking about the two very, very interesting cases I've ever seen in Kaggle. So yeah, so let's get started. So like I said, so I will be talking about two use cases. One is called Avito prediction challenge. Basically, another is called Centend customer satisfaction, something like that. But let's get started with the Avito demand prediction challenge, which was hosted by Avito. Avito basically is it's a website in Russia. You can think it as the KGG's counterpart in Russia. It's a so for second-hand used items and listings. So you can go there and post whatever you would like to sell online, and hopefully people will get interested and contact you and make an offer, and you made that offer. So voila. So like you can imagine, so their challenge, so for such a typical website, you would imagine to have some data like what is the item to list for the listing, and what is the description, and typically it may come with some images. If you can upload some images, that would be awesome, right? So this is a typical, very similar to KGG's problem. So in this computation, what you are going to predict is to take a look at some attributes provided by the Avito's, the company of Avito, and make predictions of how much interest the listing would be, right? So very similar, very, very similar to the two sigma problems that we talked about. And in fact, there are many commons between the two computations, such as, so they both use a very rich data types of data sets. And, we are going to predict the interest levels and so forth. But there's a significant difference between the two, which is the size. For this computation, if you recall the 2 sigma RainHub computation, how many records we are using? I think it was a few 50,000-ish, 550,000-ish records for training. And but in this computation, in the Avito, for the Avito demand prediction computation, you're supposed to use 1.5 million of training samples, and then make prediction on 0.5 million testing samples. And together, the data is the data is about 1.2 gigabytes. And in the meantime, there's another 1.9 million images to analyze with. And remember, so if you recall it correctly, so we didn't actually use the image data for the 2 sigma RainHub computation just because of the size. And another thing is that for that computation, the image didn't contribute a lot. So that's why we didn't talk a lot about that. You have to leverage, how to take account of the image information to come up with a better model. But in this computation, we're actually going to use the image, the 68 gigabytes of images to help build up the model. And in the meantime, so another interesting is, so in the meantime, so you are provided with a larger unlabeled data. What does that mean? So it's in the same format of training data, but the difference is it's unlabeled, right? It's unlabeled. So one thing you can think about is how can we come up with the unsupervised learning approach to take advantage of those unlabeled data, right? So, and which makes it together, they make it this computation pretty much interesting. So another thing, so I think I mentioned it before. So this computation, like the 2 sigma RainHub computation, it uses rich data types of data set. So it comes with numerical data, categorical data, date time data, image data, and text data. Text is another interesting attribute for this computation. In fact, image and text are critical to this challenge, as so which is different from the 2 sigma RainHub computation we've already seen, where we primarily still see it as a tabular-ish data set, which means so we don't have to deal with image. We only need to spend a little bit effort on the text and so forth. But in this computation, again, the image and text are critical. So how does that mean? So if we take a look at the images on the right-hand side on the top, so there are some, on the top, you can see 3 images. So in the center, so in the bicycle, all the 3 images are about bicycle, right? So, but if you have to guess, if you have to make an offer, I guess you probably would be interested in the middle one instead of the left-hand side and the right-hand side one, right? Because the image in the middle is authentic. It has nothing else than a bicycle, right? And the image on the right-hand side is probably too poor in terms of quality, right? You can hardly see the bicycle from the image, and not to mention the messy the mass on an image. And on the contrary, the image on the left-hand side is probably too glossy, right? So it's too fancy. It may not be authentic. And I cannot see the details, right? What is the specification, what brand, and what types of bicycle it is. So it's hard to see, right? So, and which makes it less trustworthy. And same thing for the description. There are some descriptions that are very accurate precise and concise, informative, like the one in the middle. But there are some poor descriptions, such as it contains it contains less information, or it's a little bit fishy because it's so bluffing, it exaggerates the fact, which amazing, watch for sale, don't miss up deal. So this description doesn't really sound authentic or genuine, so which may make the interest level low for the entire listing, right? So but how can we extract this kind of information out of both images and the text, which is a huge challenge for this computation. So for this computation, we've seen two major approach using different algorithm. Like in many other computations, so GBDT, like algorithms such as Light GBM or XGBoost and Light CAD Boost, is still the go-to choice by most winning teams, as they typically work better on datasets that consist of heterogeneous features such as the numeric, categorical, and different types of features. But in this computation specifically, the champion team, to most of the team's surprise, they primarily used a deep learning based approach to help them stand out. And fortunately, in a post-computation sharing article, their team need Kaggle Grandmaster Leaderboard, by the way. So Leaderboard, his real name is Xiaozhou Zhang, and he's a graduate student from the University of Alberta, if you're interested. So, and so basically, Leaderboard shared the solution they used for this computation, and which blew the mind of their teams, because we had never thought of it's impossible to create a purely deep learning based approach for such a type of challenges. So that's really mind blowing, and this is what I'm going to share as of today. So let's take a quick look at the different approach, right? So the conventional, on the left-hand side, we're talking about the conventional approach. And what we discussed, so for the conventional approach, we will get started with the feature engineering, then model tuning, and model ensemble, right? I'm not saying there's nothing important for deep learning approach, but for deep learning approach, so instead of spending lots of time on feature engineering, and we probably do the same thing, but make the same effort, but with another focus on network architecture design. So we will be diving into more details in later. But so here, what I'm trying to say is, so feature engineering is the core for the conventional approach. But the network architecture design is the core idea for deep learning approach, followed by data augmentation and training procedure tuning. You don't have to, if these terminologies are aliens to you, don't worry about that. So, because so you probably don't need to do that right away. But if you know, so the data augmentation, training procedure tuning is important for deep learning. That's good enough. And so what's special in that case? So from the practical point of view, if we follow the conventional approach, again, so we have to spend a fair amount of time on feature engineering, how to deal with the data, how to prepare data, how to come up with more representative features. That's basically what the feature engineering is doing. The challenge is, the problem is, this requires expertise knowledge in the specific problem, or in other words, it requires a fair amount of domain knowledge and the knowledge on how to process the data, and as well as the algorithm you're going to use. So therefore, you got to have a very good knowledge in every single aspects, and then to allow you to come up with meaningful feature engineering and improve the solution there, and hence improve your solution. So, but not everybody. So think about it. If you're a data scientist, you probably have to switch context between the project you have to work with, right? So in one day, you probably need to work with NLP, well, not customer churn problem, and then the next day, so you have to jump into a network optimization problem. So to be fair, we don't have, we can't be expert in every single domains, right? Which doesn't make sense. But and therefore, how can we come? Is there a neutral approach that will allow us to, so to come up with a fair solution, despite regardless of how much knowledge we have in a specific domain? And the deep learning is that answer, right? So instead of spending time on feature engineering, you got to think about the problem, and think about what kind of network, what kind of deep learning building blocks that can be used for the specific problem. This is a fundamental difference between the two approaches. And to be fair, so I've seen lots of companies for the past few years. I've seen more and more companies. They are, so once they get started with the deep learning designs, and they probably, started with some models, and most likely random forest attributes models. But I've seen more and more companies that they are starting to convert, to migrate the model from a more conventional machine learning based approach to the deep learning approach, just because the deep learning approach is more elegant and is a more adversarial, and so versatile, and therefore can be generalized for different kinds of problems. So this is a fundamental change, and we are so excited about this, so this trend. But it was until this computation I finally personally see the potential of using a full deep learning based approach for real problem. So yeah, this is what excited me by the the Littlebot solution. So next, I'll be talking about some difference in terms of dealing with different types of features. And we are first started with the categorical feature. We had discussed how to deal with the categorical features in our very first, actually our second session. We talked about the one-hot encoding, which converts the categories into binary representations. And we talked about label encoding. We talked about using the count of each category to represent the categories. And we also talked about a very interesting approach, which is called target encoding. So those are still valid for deep learning models. But for deep learning, we can actually use a very special type of a layer or building block, which is called the embedding layer for categorical features. So the embedding layer is actually inspired by word-to-vec, the concept of word-to-vec or word embeddings. So essentially, we'd like to convert each level of each category, a category feature, into vector representations. So in below, I just give it a quick example. So if you take a look at the category, puppy, dog, kitten, cat, and so on and so forth, we would like to come up with embeddings. By embedding, I mean, so here I'm just using a three-dimension in vectors as for example, right? So for puppy, we convert it to 0.9, 1.0, and 0.0, and the dog 1.9 and 0.2, and so and again so 0.1. And so on and so forth. So if you have to guess, so given that there, there are just a few categories here, and the dimension is a very number of dimension is just a 3. We can have a guess on the actual physical meaning of each dimension. For instance, the first digits in the vector is probably indication for whether it's a dog or not, right? So, and the puppy, and you'll see puppy and dog have a value close to 0 or close to 1, right? And the second digit probably talks about the age, right? How mature mature of the the animals, right? So, and being 1 means it's a so a baby, puppy, or kitten, and if the value close to 0, it indicates so it's a so the adult animal, and the last digit stands for a cat, right? But in fact, so in practice, we would use a larger number of dimensions for in practice, for instance, 300D dimension. In that case, it's hard to guess the so the actual physical meanings of each digits of each scalar in the vector. But so you get the idea, right? So we want to convert the category into a dense representations instead of a sparse representations, and unfortunately, so we can use a predefined deep learning layer embedding, and using that embedding to deal with the category features. So, and putting it together, by adding into a deep learning neural network, so the embedding layer will automatically discover the hidden patterns of for the specific categorical feature. So this is how we would deal with categorical features for deep learning models. And another thing is text, right? So we also talked about in the previous sessions. So we also talked about so how to deal with the text data. We can use a word frequency, like counting the frequency of each word, and use sort of a IDF algorithm to penalize the frequent words, and so on and so forth. And we also talked about word embedding, right? So word embedding can be used for both models, but they will be used in differently. So remember, let's say if we need to encode a sentence instead of a word, right? So a sentence contains many words and in a sequence manner, and if we are going to use the word embedding for the conventional approach, we got to encode the entire sentence as a row, right? And and therefore we have to aggregate the embeddings for each word, and most likely we would do so the average on the embeddings for each individual word. And in that case, there might be information lost during the process, because so by aggregating things, we we disregard the, so the sequence information, and we disregard each individual word meaning. We just simply average everything together. And if you think about the, so the meaning, so if we switch sequence, switch the sequence of two words, we could end up with totally different meanings, right? So it's not hard to imagine. But so in that case, if we are doing it in that way, so yeah, so there might be information loss. But on the contrary, so if we are using, in the way we are using word embedding for deep learning model is through some sort of a sequence model. By sequence model, what does that mean? So you don't have to, if you don't know the details, don't panic. So you don't have to know the very specific details. But the rough idea is, so we will through each individual word embedding as an intermediate status and through them into a sequence model. And during this process, the sequence information will be persisted and will be leveraged and will be utilized for the model. And as well as, so each individual word embedding information will be used as is instead of being aggregated. So essentially what I'm trying to say is that there will be little to zero information loss by using the word embedding by using the information with the sequence model. So this is much better, and the problem, the improvements is so significant by using a sequence model. Imagine image is another types of data we would like to use for this computation. So if we have to use a conventional machine learning algorithm such as XGBoost to tackle for this specific computation, we have to extract the image information in a way that they can be used by XGBoost, right? So typically there are a few things you can do. You can first of all use a pre-trained classification model to make predictions on what is in the image, what the image is about. This is called classification, right? So another thing we can do is to apply object detection on the image, and it will tell us what objects are on the image instead of telling the class of the image, right? So imagine, so if we take a look at the images on the right hand side, for classification, it will only tell you, okay, so even though there are one cat and one dog, or two cats, one dog and one duckling on image, it will only tell you, okay, so because the dog occupies the majority of the image, so it will just simply classify it as a dog, right? So, but in fact, there are multiple objects on the image, right? So that's why if we apply an object detection algorithm on the image, it will tell us that there's two cats, one duckling, and a dog on the image, along with their bounding box. That is called object detection. So we can apply the object detection algorithm to tell, okay, so how many objects and what are the objects on the image, right? Therefore, we can come up with some sparse features, and pretty much like the one-hot encoding, we'll use one column to indicate if the image contains a cat, or even how many cats on the image, so on and so forth. Yeah, so this is one way to do that. Another way is, so we can also use so if we take a look at the pre-trained deep learning neural network, so demonstrated in like what's showing on the bottom image on the bottom right image. So you can see the last of the two red layers, they are called bottleneck in CNN model. So instead of using the final results, which would output the classification result, we can use the bottleneck as for features. Because so if we threw an image into the pre-trained neural network, so it will predict. So if the last layer will predict the actual classes, but the second last layer will output a 1 plus 1 by 1 by 4,000 vector as a feature. So then we can take the 1 by 1 by 4,000 vectors as the features for the image. So in that case, so we are actually using the pre-trained deep neural network not for classification purpose, but for encode. Use it as an encoder to encode the image, right? So this is how we would do with the images if we are going to use the conventional machine learning algorithm. In the meantime, so we can use a deep learning approach, right? For sure. So we can use, if we were to develop a deep learning model for that case, we just need to add a building block, a pre-trained neural net CNN model as a building block, and put it into the entire deep neural network architecture, and using it as a building block to deal with the images. So this may sound, so I hopefully so by far you get some ideas of the difference between the conventional machine learning approach and the deep learning approach. But so you may still be a little bit fuzzy about, so what exactly we're going to build out by the end of the day. So here's the thing. So here's the architecture proposed by Littleboat, and I was able to replicate the same architecture, and it turned out, so if I had known this architecture, so our team could have, and using that as a to improve our model, our team could have got a gold medal in that competition instead of a silver medal. But so, which is super exciting and so powerful. So yeah, we probably need to. I'm going to walk you through with the architecture and see, so how, so we can put together a giant neural network and with different branches to deal with the different types of data. So first of all, the way to read it, this is diagram is not from the top to bottom, but in a different but in the reverse direction, which is from bottom to top. So you can see that, the directions indicated by those arrows. So I will get started with the column, bottom left column. So which is a categorical branch. By categorical, so they are actually using an embedding layer to deal with the different categorical features. So for each categorical feature in this data set, so we will need to throw them into an embedding layer, and for the embedding layer to take a look at the category feature and come up with the vector representations like what you were seeing in the previous slide. And after the embedded layer, so the data will be the output would be vector. Then we threw them into a dense layer. By dense layer, it means a fully connected layer. So, and then we combine everything together. We can calculate all the dense layer, the dense representations. For instance, so if we specify the vector size to be 100, right? So, and by the end of the day, the region will output 100 dimension, 100 vector, 100 dimension vector. Embedded, city will output, will be converted into a 100 dimension vector, same, and so on and so forth. So say if we have 5 categorical features, so we would end up with 500 dimension, 500 dimension vectors, and then we threw them into a dense layer, and we could furthermore reduce the dimension. Say if we reduce the size from 500 dimension into 100, then we will throw them into a second layer of dimensions, and here we will be doing a calculation with the other outputs from the other branches. And so that's for a categorical feature. And for numerical feature, there's nothing special here. So just bring all the engineering, the fancy, amazing engineered features and throw them into a numerical, a dense layer, and do the same thing and calculate it with the outputs from the other layers. And the image is a little bit interesting, right? So here, for every single image, we will throw them into 2 deep CNN models. One is called VGG16, and then it's called ResNet50. These are some of the most common CNN architectures. So, and fortunately, we've already, so the people have trained the model against the ImageNet, which is a huge image data set. So therefore, the pre-trained models have somehow embedded the images information from the image, large image data set. Therefore, we can use them to further train the model, to improve the model, and to make the model more suitable for our problem. So essentially, so each CNN model will take an image and convert them into a vector, So, and again, so we will be do an average pooling of the output and throw them into a dense layer. Then concatenate the outputs along with the outputs from the other branches. And for text, that's the same thing. So, but instead of throw them into CN models, we will be using sequence models here. So we will be using a 2-layer LSTM to deal with each of the text features. And by the end of the day, so we just need to, so what I need to do is, okay, so just concatenate everything together and throw them into a binary cross entropy layer, which outputs the, which makes it a final, classification. So essentially, what I'm trying to say is, so here you can see, so instead of doing a lot of feature engineering, we didn't do much engineering. So if we can do a feature engineering here, that would be awesome. But if you don't do that, that's not the end of the world, right? Because you can use different, what basically you are doing is, instead of doing a feature engineering, you are choosing different types of architecture and to deal specific type of data, and simply calculating everything and putting everything together. So we end up with a large complex deep learning model. But in the meantime, So it may sound complex, but it's actually simpler than the conventional way, because for the conventional way, again, so you got to do feature engineering, to extensively spending a lot of time on feature engineering, which could be time consuming, let alone, it requires expertise, knowledge in the specific problem. So yeah, so that's why we're super duper excited about this approach, because so it minimizes the necessity of minimizes the requirement of so the domain knowledge to be able to, for us to be able to come up with a decent model for real world problems. So that's why we are super duper excited about the idea. So hopefully it gives you some ideas about the trend on so how we gradually transit from a conventional approach, machine learning approach, to a more modern deep learning based approach for some real world problems. So that's for the Avito demand prediction use case. So if you have any question from the audience, like if you have any questions on the architecture, on the details, how to deal with the images, how to deal with the text, and so and the architectures. If you have any questions, feel free to raise your hand. Okay, it's being a little bit quiet today. Okay, never mind. If you have questions, just so let me know anytime. Okay, feel free to stop me if you have any questions. But if you don't, so let's move forward to the next use case. Okay, so the next use case is called Santander customer transaction prediction. In this computation, you are challenged to identify who will make a transaction by looking at a very, very interesting set provided by Santander Bank. So let's get move forward. Just a warning. So this has been the most interesting. Well, first of all, it's the most participated computation in Kaggle's history. So more than 8,000 teams participate in this computation. And the 8,000, I believe there are more than 10,000 individuals joined this computation. And arguably, this is the easiest and the hardest computation. So by easiest, what I mean is, so everybody can jump into the computation and get a decent result, even with a simple model such as a naive Bayesian or logistic regression. You can easily get ROC AUC 0.88, so with no effort. But most of the people got stuck there. Only 5% of team could go beyond the ROC AOC of 0.9, including us. And our team eventually won gold medal with a rank of number 17 in this computation. But in order to get there, we've gone through a long way. So to be honest, so during the computation, I literally had dreams. In my dream, I'm still, so trying to figure out the myth and trying, what's the problem it is, and what are the magic features? Where is it? How can we find it? Did I miss anything? So I had a lot of a dream, so related to the computation, and after the computation, I felt I lost a lot of hair. So yeah, you can imagine so how challenging this problem is. So go back to the problem. So you're provided with, again, so you're challenged to predict, so the customer will make a transaction or not, which makes it a classic binary classification problem. But so we haven't talked about the data, so that will be the next thing. So we will see. So pretty much like the previous any other computation. So the first thing we would like to see is what are the data? What does the data look like, right? So, and trust me, this is gonna be the most interesting dataset you've ever seen. Okay. So first of all, you are provided with 200 numeric features and a binary target column and the string ID code column, which will serve as the unique identifier for each individual row. And your task is to predict the value of target column in the test data set. And again, so this is a classic binary classification problem. So everything sounds normal, right? It's straightforward so far until if you dive into the data, you'll find something interesting, like there's no missing values. There's no missing values. There's no nulls. You don't have to impute the missing values. And wow, this sounds good. It sounds nice, very, very, very nice. And the second of all the features are almost perfectly normally distributed. I don't know how you feel about that, but to me, when I saw that, I was like, this cannot be true. This cannot be true. How comes a data set could be so perfect, right? So no missing value and not every single variables are normally distributed. And that's not the end. That's not all. And all the features are almost linear correlated with each other. No multilinearities existing in this data set. And train data and test data follow almost the identical distributions. So to be honest, this is sounds the dream, the perfect data set every single data scientist would dream of, right? So trust me, believe it or not. So in real world, so you got to the data set you got to deal with will either contain missing values or so you have to process in a way that the distribution will become normal and so on and so forth. You can never get a perfect data set like this one. So this is the first reaction. Pretty much every participant saw the data set. What the heck this set is doing, and how Santander come up with such a weird data set, right? So these are some thoughts and reactions that people would generally have. But that's just the surface of the data. So if after spend 2 months, after 2 months of the spending time on the data set and the problem, so we hit the wall. We hit the wall because it's really, really weird. Typically, so you expect the more complex algorithms such as LightGBM or XGBoost perform way better than simple ones such as Bayesian, naive Bayesian, logistic regression. But in this case, in this computation, you'll find that they both, the complex model and the simple model, they all get the similar result without fine-tuning. Or even you fine-tune it, so the improvement is very, very minimal, insignificant, right? So, and another thing bugged me a lot is none of the feature engineering ideas tried actually worked. None of it worked, regardless of what kind of feature engineering I come up with. They just didn't work. They just didn't work. None of it worked. This is so encouraging and so frustrating. And I don't know how would you feel something like that, but imagine you know you are the expert in a domain, but after spending 2 months of effort on a problem, you just can't improve it. You just can't get a better way around it. So that's super duper frustrating for sure. And another interesting finding I would emphasize is, and so I would like to bring up is the best light GBM model only requires 2 leaves. What does that mean? So every time you generate a decision tree, you only need 2 leaves. And more than 2 leaves, having more than 2 leaves will make the model worse. So again, so it sounds like the data is good enough. Therefore, so even with a simple model, we can get a decent result. We can get a decent result. So at this point, people started wondering that with this computation, is this computation going to be a war of stacking? Right, so because so if feature engineering didn't work and model tuning didn't work and the code ensemble work, right? So because so we've already seen before that ensemble is a very nice way to improve the model. So, however, it didn't work neither. It didn't work neither. By assembling, by averaging the result from different models, so we end up with almost the same result. Or in other words, ensemble didn't help at all. So what can we do? What can we do with such a perfect data set and so we where we can do pretty much nothing did quite actually help, right? So how can we do with that? So this has bothered me for a long time during the computation. But so let's I would use this computation as a perfect example to see that despite of the advancement in algorithm and despite of the so the techniques and so tools and tricks so on and so forth, what is the fundamental competitive advantage for a good data scientist, right? So you can so some of them may name the knowledge in machine learning, the sense of data, the domain knowledge, and these are valid answers. But to me, the fundamental competitive advantage every single data scientist got to have is the sense of data. And the ability to make sense of data. So I would like to use this computation as an example to explain how the sense of data actually helped us get a gold medal in this competition. So let's take a look at I forgot to mention something is more confusing or scary. There's synthetic data examples in the test data set. What the heck? So what does that mean? Let's take a look at some examples. So this is a distribution for one variable, one of the 200 variables in the data set. So what did you observe by looking at the two examples? What did you observe? So you'll probably see there are more peaks on the test data set as more unique values in the test data set than what's in the trained data set, right? But they are still of the same distribution-wise. So they are pretty much the same. But so apparently there are more unique values in the test data set. So, and we observed that. I observed that, and my teammates observed that as well. But How can we make sense of that? What does that mean? What does that mean? What could be the reason of having such a difference? One of the guys from the Kaggle community come up with a genius hypothesis. Let's take a look at what is the hypothesis and how does that mean. So he or she came up with the assumptions such as there are fake data, there are synthetic data in the test data set. And how can we tell if whether or not they are faked? Because so his assumption, his hypothesis is that there are some values in the test data set. They were generated by a sort of a simulation process that uses a distributions estimated from some samples which were not included in training of this set. So it may sound a little bit wordy, so let me explain what is my interpretation. So imagine you're going to do a simulation process. What you are going to do, what you would do, right? So you probably want to take a look at some kind of data, right? So for instance, if you are going to create a simulated data set for a class for school, let's say for elementary school, on the ages, what you are going to do, right? So you probably want to take a look at the ages statistics on ages of other schools, like so in Calgary, right? So how many students in elementary schools are of the age of 12, and how many of the age of 13, and so on and so forth, right? And then you come up with the distribution of age, and then you can use the distribution of age to estimate to simulate come up with a simulated data set, right? So, and first of all, you got to have some sample to calculate the statistics needed for simulation, such as the mean of the data set and the standard deviation of the data set, right? So, and with the estimated distribution, then you can do the simulation, right? You can do the simulation. But the problem is, so if the original data set, the simulation is I wouldn't say discrete. Let's say they have the data is a discrete with enumerate, right? So there are a handful of actual values, but by estimating the distribution, by estimating the mean and the standard deviation, and using estimation to simulate the data, you end up with a continuous data, not a discrete data, right? So therefore, you end up with more unique values. You end up with more unique values if the data was simulated instead of the actual data, right? So that's the hypothesis. So there are some samples in the test data, their results are from a simulation process, which is from estimation from some samples, but the samples used to calculate the estimation were not included in our training and test data set. That's the assumption. So I'll just pause it for a little while. So just so in case you have any questions, and because this is this is very important assumptions, and we will be seeing it later. But I just want to make sure everybody understands what the assumption is and what are we going to do. Okay, any questions? Okay, all right. So I assume so you all understand what the assumption is, and I will just move forward. So with this assumption, and next question is how can we identify the so to prove it, whether or not it's true, and how can we identify the fake data set from the test data. Okay, so let's say if the assumption is true, then given example from the test data set, we can go over its features, the 100 features, so the 100 values, and check if the feature value is unique across all the values in that feature, on that feature. If at least one of the examples of feature is unique, then the example must be a real example. So again, so this may sound a little bit complex, but let me explain. So say we have let's take a look at one example from test data, right? It contains 200 values, right? Corresponding to 200 features. For each feature, it has a value, right? So, and we will iterate the 200 features. And first of all, let's start with feature 1. And we will take a look at the specific value, say if the value is 10. And then we will take a look at if 10, how many times 10 occurred in feature 1, right? So, and if the occurrence, if 10 as a value only occurs one time in feature 1, then okay, the entire example is real. It's real, right? So because it is real. Or if we find, so all the features, all the, so for example, all the features, all the values out of the 200, they have more than one occurrence in corresponding feature, right? Then it must be a fake data. So in that, we can apply this criteria on the test data, and here's the piece of code to do that. So if we iterate it and apply this check on the entire test data set, guess what? We end up half being identified as the fake data and half being identified as the real data. It can't be a coincidence, right? So if we see something like that, it just cannot be coincidence, because it's too good to be true. If we, so if the hypothesis is not true, we can't get such a coincidence, such a, so a perfect example is half being fake data, being, so real data. So therefore, we have a solid reason to believe the assumption or the hypothesis is true, that there are fake data as well as real data in the test data set. And we got a way to differentiate them, so which are real data, which are fake data. So, but this actually adds the complexity, adds the confusion to the problem, because so what? We know you tell us that there are fake data, but how does that help for the problem? How can we leverage utilize this finding to improve our solution? So by far, the answer is no, we don't. I didn't know the answer. I didn't know how to leverage information. What I know is, there are fake data, and I can't think of why they wanted to put the fake data in the data set. So, but let's just put it to the back burner for a little bit of a while, and let's take a look at the other things. And I will go back and explain. So how to leverage, utilize this finding to improve our model. But again, okay, so there's something even interesting and even scary. Okay, so after a few days, another guy who discovered that a more scary thing. if we randomly shuffle the data, that won't change the result at all. What does that mean? So let me explain. What does that mean. So let's say for every single sample in the data set, in the training data set specifically, let's randomly switch the name, switch the value among the 200 features. For instance, the normal sequence is variable 1, variable 2, and all the way to variable 199. However, if we randomly switch the sequence of the variables, and we do it on every single example in the dataset. So, and using the shuffled data to train our model, we end up with the same result, the same comparable accuracy AUC/ROC on the validation as well as on the leaderboard. This is insane. That doesn't make any sense at all, but it happened. To be honest, even for today, even as of today, I still couldn't think of why. So this happened. This could be true, because this just is nonsense. You can't switch features, right? So you can, for instance, it's like, so we have this set, we have age, we have income, and we just randomly switch the age and the income. So we end up with the same result. That's just insane. But it is what it is. It is what happened for this specific computation. And then now started worrying about my hair because I scratch my hair too much. And so I explain how can we leverage that. So there are this is actually something that can be utilized to be leveraged to improve the model. This turns out to be a good thing, but I explain again, so I'll explain it later. But remember I talked about, so the fundamental competitive advantage for a data scientist is the ability to make sense of data. And so we finally got there. And I'm going to explain how can we make sense of data from a data scientist perspective. So there are some fundamental things that we got to do, we missed during the the first few weeks of the computation. So here I'm showing one of the example, one of the variables, so the variable 198. This is a typical variable, so pretty much like they are the variables. So if we take a look at the variable only, so we would see, so it's perfectly normally distributed. But if we color-coded the different classes, orange being 1 and blue being 0. So we would notice that there are actually a slight difference between the two distributions, between the two classes, right? So, and the orange one is lean to the left-hand side a little bit, and while the blue ones, they are a little bit right skewed, right? So therefore, if we come up with a simple approach to differentiate the two groups, we probably would just draw a straight line here, right? So with the close to 11 or 13 and something like that. So, and if we it's actually 13. So if we draw a line on 13, so we probably see, and then we calculated the probability of 2 targets. So, and then we'll probably say, okay, so if we draw a line on 13, so for all the samples with the value is less than 13 on variable 198, the probability of the target is 0.10. And for the record for the examples that have greater than 13 on variable 1998, so the probability of the target is 0.118. So that gives us not perfectly, but somehow a sort of a, so the cut on the discriminations on the dataset. It's not perfect, but there's something. And if we combine the effect of from the other 200 variables, so we end up with a decent classifier, right? So this is what we observed. And on the left-hand side, I just color-coded it. I just plotted it in heat box way. So you can see, so the color is more darker. It's more darker on the left-hand side, which means that there are more ones than zeros on the left-hand side, right? So this is what we can observe. So we can observe normally on a variable, right? So yes, there are some minor things, but this is probably the big picture we can see. And keep in mind that here we are using a distribution plot or histogram plot to help look at data. And to be honest, the histogram plot has lots of advantage. So such as, so it gives us a big picture of the distributions and so forth. But somehow, if we only take a look at the big picture, we could lost the, lost some, so the detailed information or the details. So therefore, we got to take a literally closer look at the data. So if we zoom in this blue area, so which is in a range of between 11 and 11.10, right? So let's just focus on this very, very specific range of data, and doing the histogram plot again. But this time, instead of so aggregating the data into bins, into histograms, so we'll be actually counting the frequency for every single value. But we didn't see this sort of like a barcode thing. If we take a look at the big picture, we can only see that by zooming into the very, very fine granular details, right? So, and in that case, so you would see some patterns, right? So, who can tell us, so what did you observe by looking at this barcode-ish dataset? So, who would like to share your findings by looking at what patterns you can see, you observed? Anybody would like to share? Okay, never mind. So I explain what does that mean. Okay, so every single bar indicates a value in the data in the range of 0.11 to 11.10, and we see different observations, different patterns of frequencies, right? So most of them only occur one time in the dataset, right? So which is the lower bar, so with a frequency of 1. But some of them come with a frequency of 2 and 3 or 4 and so on and so forth. If you observe the counts, you will see the same patterns, right? So 11.0689, it occurs only one time, but the others, the one close by it has 2 occurrences, right? So this is what we could observe by taking closer look at the data. But what's the problem? What could be wrong? What could be wrong here? So it seems to be normal, right? So it doesn't there's nothing wrong with so having different occurrence or different frequency on values. So it doesn't seem to be abnormal. But let me tell you, there's something. This counts actually the magic feature in this computation. And this is a breakthrough of the computation. If you could decode the mysterious behind the thing, yeah, voila, you got a medal. You got a medal. If you can crack more, so you got a gold medal. So that is why people are calling this computation as an enlightened computation, as compared to so some computations you are accumulating the so improvements. But in this computation, there are just a few steps. You got to do a few steps, then voila, you got a gold medal. So, but this is what I'm showing here. The magic feature is the most important findings or the most important mysteries in this computation. So let me explain. So what is the magic feature, and what can we, and how, what at the interpretation, how does the magic work? So we've already seen, so the distributions, right? So, and after the original dataset, and we take a close look at the data. But if we could come up with so on the bottom, I come up with distributed plot, exactly the same as the one on the bottom, but the heat map is a little bit different. So the difference is that, so I included the count of each value in the dataset. I included the count and frequency of the value. For instance, this one, I included the value of the count as the y axis in the heat map plot. So all of a sudden, there's something new occurred. So if you take a look at this area, right? So what does that mean? So so not only the value itself matters, but also the frequency matters. So the more frequent a value could be, the more chance it could be, the target could be 1. The target could be the 1. So this all of a sudden increases the information we can have. We can have this, or in other words, this magic feature, the count of the value, count of each value. So all of a sudden becomes the magic feature in this computation. So by including this feature into the model, so now the decision tree can see something like, instead of say, okay, so let's draw a single line here, right? So it will say, okay, let's draw a line here, right? So let's draw a line. First of all, let's draw a line here. Then draw another line here. So we end up with a more accurate model. So in fact, if we include the original value and as well as the count of values as the magic feature, we only use those, the variable 198 and the count of values from variable 998. So, and using the two features to come up with the model. So the accuracy could get a significant improvement. So, and if we apply the same thing on every single 200 variables, so we could significantly improve our model from 0.9 to 0.10. So this may sound a little bit bizarre, but in the next slide, so I'll be explaining why. So why this works, actually works, and then a few things we actually did, we actually done to further improve our model. So first of all, so with the magic feature of the LTM boosted the AUC-ROC from 0.9, which is equivalent to the top 400 in this computation, to 0.2 or 0.910, and we substantially moved that rank by 200. In the meantime, we also applied a few additional tricks, which eventually got also gold medal. So here's the things. So first of all, reverse missing value imputation. Remember, we made the assumption that there are fake data samples in this set, right? That they were generated using distributions from the samples out of train and this. So is it possible that, so this made us wonder, is it possible that's the same thing in the training data set? Or in another word, so could there be some, you know, sort of a fake data in the training data set? So, and therefore, the next thing we did is actually, so we come up with a new, so remember we come up with a new feature, right? So for every single variable, we come up with a new feature, which is the count of the values of the variable. So then we did the same thing, but instead of counting the frequencies, so we did it a little bit differently. So if the frequency is 1, we would mark it as 1. But if the frequency is greater than 1, we mark it as null. We mark it as null, the missing value. What does that help? How does that help? So that helps because, you know, so by converting, by leaving those values being 1 where the frequency is 1, so we see them as a, you know, so the, you know, so sort of a, you know, frequent data and frequent data. And in the meantime, so by converting the populating the values for the actual, you know, so frequency into null, we are enforcing the XGBoost and the Light GBM to treat them as a separate example, as a separate cases. So therefore, the model will further separate the two things, the frequency being 1 and frequency being not 1. So to sort of doing it in a binary way. So, but so this is called reverse missing value imputation, because typically so we would impute the missing values to an actual value, but here we are forcing the actual value into missing, and leveraging like GBM and XGBoost the capacity of dealing with missing value to make it to improve the solution. So it turned out that this actually worked quite a bit. So we, using this trick, we improved that accuracy, AUC-ROC, from 0.10 or 0.910 to 0.918. And we are already being on the leaderboard, the top 100 on the leaderboard. So then the next thing is remove the fake examples. Again, so there are fake examples in tested data, right? So, but when calculating, so we need to do when we add the new features of counting the frequencies of the values. So when doing that on tested data, keep in mind that there are fake data, right? So the fake data can cause some trouble, can decrease the accuracy of counting the frequency, because they are not supposed to be there to calculate the frequency, right? So, and then the next thing we did is to just remove the fake data from the test data and redo the calculation of frequency again. So this helped us to improve the model further from 0.918 to 0.920, and we've already been done, so the top 17. And the next thing we did is another very, very interesting trick in this computation. Remember we talked about the, so the shuffling thing, right? So by randomly shuffle the sequence of the data, the variables of the example, and creating a new data set. So we end up with a very similar result of accuracy, right? So, and the normal reaction to this finding is that, oh my gosh, I got to figure out why, because it's so confusing. This is a normal reaction of a human being, right? So, and to be honest, I spent a few days on figuring out why this happened. But so it turned out this is in vain. This effort ended up being in vain, because so I couldn't find anything to make it reasonable. But this is something I learned from my teammate, the Grandmaster Ji Wei Liu. His reaction to the problem is that, okay, so it is what it is. I wouldn't be bothered by the funding. So instead, let's figure out how can we take advantage of that. So he came up a genius idea of so data augmentation. So by coming up with a data augmentation trick, that actually helped. So the idea is quite straightforward. So, okay, so if randomly shuffling the data works, let's just randomly shuffle it again and again and again. Let's say randomly shuffling the data 5 times. And then we appended the shuffled data to the original data, and using the augmented data to retrain the model, right? So we end up having more data samples, more samples to train the model, and we know that more data will make the model better, right? So he just used the simple approach, and that gives us a further boost. So from 0.20 to and 0.920 to 0.922, and we've already got the top 50. And the next trick is so we so included some sort of a multi-head one-dimensional CNN models, and that give us the last last push to the to help us get the gold medal. So that's pretty much what we did as a team for the biggest and the most interesting and most confusing computations in Kaggle's history. And this as you can see, there are many things that's so interesting, and so yeah, so that's why I was so excited to share what we've done for the competitions with you guys. And yeah, so that's all I have for the series of the Nano course, all the way from the so how to do the data exploratory data analysis and feature engineering, model tuning, and model ensemble, and yeah. So and today we share the 2 use cases of their computations, and hopefully so you got something from there, and you can see something out of the sharing, and you can. And we enable you to get started with the actual Kaggle computations. So yeah, that's all I have. And we still have some time if you have any questions on design on Kaggle, on today's contents or the previous day's contents or Kaggle, so our design. So yeah, I'd love to address your questions if I could. So yeah, questions. You guys have been quiet today. Okay. I would assume you, yeah, you're happy and the smiling face. Okay. Yeah, thanks, Alpha. Yeah, I've been enjoying what is the next phase? No, so that's a pretty all I have. Okay. So yeah, so we're going to send out the PowerPoint right away after the session. Yep. Of course. Okay. All right. Yeah. Thank you so much. So if we have a related question in the future, can we ask you? Yeah, of course. So I'm on the Slack channel. It's just I probably didn't so check the messages frequently. But so if you want to, you can just shoot me a message through Slack, and I'll share my email address afterwards. So if you have a question, you can reach out to me through LinkedIn, through email, so whatever. So yeah. Okay, all right. So, and for next phases, well, I don't have much on the Kaggle per se, but I believe CADASA is going to release some other learning opportunities, and I would encourage you to keep an eye on the CADASA's Slack channel and LinkedIn and the website, because I know they are so the focus there are so amazing. They have so much exciting things on the way to share with the community. So stay tuned, and yes, have a good weekend, and hopefully I will see you soon for the future endeavors. Okay, thank you. Bye.